Jai Hind students, welcome to my YouTube channel. Today in this session we'll be discussing about the magnetic effects of current. Students, we have discussed flowing charge constitute an electric current, right? There are various effects of current. We have discussed heating effects of current. That was studied by James Joule. All the electrical appliances, almost all of them, which we make use of in our daily life, are based on heating effects of current. Then students, there is chemical effects of current. That was studied by Michael Faraday. And then there is magnetic effects of current as well. The magnetic effects of current was first studied by Hans Oersted. He was a Danish scientist and he, through his experiment, studied the magnetic effects of current. So before we start with the proceedings, before we start with Oersted's experiment, then we'll be discussing magnetic field lines, then we'll be plotting the magnetic field lines. That is due to a straight current carrying conductor as well as due to a current carrying loop, right? First, I would like you to watch this animation. This animation is based on Oersted's experiment. So the experiment is basically based on the fact that whenever current is made to pass through a conductor, then magnetic field is established around its vicinity. That is, magnetic effect can be experienced around a current carrying conductor. So as a result, if a magnetic compass needle is brought near a current carrying conductor, then the compass needle tends to give some deflection, which indicates the presence of magnetic effect in that region. So this is known as the magnetic effects of current story. So before we discuss further, please watch this animation.
The space around a current carrying conductor in which its magnetic effect can be experienced is called magnetic field. In 1820, the Danish scientist Oersted discovered the magnetic effect of electric current. This is a simple experimental setup so as to observe the magnetic effects of current. It consisted of a magnetic compass needle NS, a conducting wire AB, source of EMF, that is battery, a reversing key which is also known as commutator, and a rheostat. Oersted found that when a wire AB carrying current was held over a magnetic needle NS such that the electric current passed from end B to end A, then the magnetic needle showed some deflection. That is, when the current is passed through a conductor, it modifies the space around the conductor. On holding the wire below the magnetic needle, the needle got deflected in the opposite direction. It indicated that magnetic lines of force below and above the needle are directed in the opposite directions.
So students, what were the observations during Oersted's experiment? Number one, if a magnetic compass needle is placed near a current carrying conductor, then the compass needle tends to give some deflection, indicating the presence of magnetic effect around the vicinity of the current carrying conductor. That's the first observation. Second is, student, if the direction of the current in the conductor is changed or it is reversed, then it is found that the compass needle tends to give deflection in the opposite direction. That's the second observation. And third, student, if the magnitude of the current flowing through the conductor is increased, then it is found that the compass needle tends to give deflection through large amount. So we can safely conclude that magnetic field is produced around the vicinity of a current carrying conductor. And the strength of the magnetic field at a point near a current carrying conductor, it increases with the increase in the current flowing through the conductor, right? And as the observation point is taken further away from the current carrying conductor, then the strength of the magnetic field keeps on decreasing. So that we will discuss later on. It obey inverse pattern. So students, that was regarding Oersted's experiment. Now before we start further, before we discuss the graphical study, or rather the diagrammatic study of magnetic field lines due to a straight current carrying conductor or due to a current carrying loop, we need to first make ourselves familiar with the magnetic field lines. Now student, look, magnetic field lines, it's a hypothetical concept, it's an imaginary concept. This concept has been developed so as to visualize the magnetic field in a given region. These are basically the imaginary lines along which a hypothetical or an imaginary north pole would move if it is free to do so. Obviously, magnetic monopole do not exist. It's a hypothetical thing. If a unit north pole is placed near a bar magnet, then it will tend to move along the direction in which the magnetic field lines are directed. Clear, students? So magnetic field lines are the path along which a unit hypothetical north pole would move if it is free to do so. Right? So magnetic field lines, basically we'll study in the next lecture that magnetic field lines, it is in the form of continuous closed loop. In the case of a bar magnet, outside the body of the bar magnet, the magnetic field lines are directed from north to south. And inside the body of the bar magnet, it is directed from south to north. But anyway, we will discuss about the magnetic field lines, about the properties of bar magnet in the next lecture. Here presently what we are going to do is, we are supposed to represent diagrammatically the magnetic field lines due to a current carrying conductor. Right, students? And for that, we need to be aware of a particular rule, which is known as right hand thumb rule. So, we'll discuss first right hand thumb rule. This rule is used to determine the direction of the magnetic field due to a current carrying conductor. Right? So, what this rule states is, suppose this is a current carrying conductor and current is flowing in the upward direction like this, along the direction of the cap of this marker. Right? Current is flowing along this direction. So, right hand thumb rule states that if we grasp this current carrying conductor in the palm of our right hand, such that the thumb points towards the direction of flow of current, then the direction in which the fingers curl, that will give us the direction of the magnetic field. Students, magnetic field basically is the space property in which a hypothetical pole tends to modify its surrounding in such a manner that the magnetic effect can be experienced in that region. So magnetic field is a space property where the magnetic effects can be experienced. And magnetic effects is experienced round in the vicinity of a current carrying conductor or in a region near a bar magnet where the magnetic field is present. Right, students? So, this is suppose a conductor. This is a conductor and current is flowing along this direction. I stands for the current and this arrow indicates the direction of the conventional current. So in this case, as per this rule, I will try to hold this current carrying conductor in the palm of our right hand in such a manner that the thumb points towards the direction of the flow of current. In that case, the direction in which the fingers curl, that gives the direction of the magnetic field. So over here, the magnetic field lines would be like this. It will be like this. It is represented by dotted lines. It will emanate from this end and it will terminate along this. And actually, it will be in the form of continuous closed loop. So if the current is flowing along this direction, then applying this rule, the magnetic field lines will be along this direction. It is in the form of closed loops. So magnetic field lines, they do not have any starting point, nor do they have any terminating point. Right? So these are the magnetic field lines. I will represent it diagrammatically. And if the current carrying conductor is like this, if the current is flowing in the straight conductor in the downward direction, then I will apply this rule like this. The thumb it must point towards the direction of the flow of current. In this case, the fingers, they are curling along this direction. So this indicates the direction of the magnetic field lines. In this case, the field lines are in the clockwise direction. In this case, when the current is in the upward direction, the magnetic field lines are in the anti-clockwise direction. Clear, students? So, in case the current is flowing in the downward direction, like this. So, again I am stating the rule. Right hand thumb rule states that if we grasp the current carrying conductor in the palm of our right hand, such that the thumb points towards the direction of flow of current. In that case, the direction in which the fingers curl, that will give us the direction of the magnetic field. So in this case, it will be like this. Like this. In this case, it will be in the anti-clockwise direction. In this case, it will be in the clockwise direction. Clear, students? Now, we will represent certain notations for it. Suppose this is point P, and let us consider this to be point Q, right? Here, what will be the direction of the magnetic field? How to write it? How to represent the direction at point P? So here, what will happen is, the magnetic field lines from point P would be given by drawing a tangent at point P. So it will be in the outward direction, right? As we are aware, whenever the field lines are curved, then the magnetic field at a point is given by drawing a tangent at that particular point. So here also, the field lines are like this. These are the field lines. So this is where point P is. So from here, magnetic field line is like this. So field line is going like this. So if you draw a tangent over here, it will be like this. So as a result, the magnetic field at point P would be perpendicular to this plane, which in this case is the plane of the whiteboard, and directed outwards. Why at point P, Q, students? Here, the field lines are like this. Point P is located somewhere over here. So here the field lines are entering. So at this point Q, the magnetic field will be directed like this. So it will be perpendicular to this plane and directed inwards. Clear, students? So at point P, direction of magnetic field is perpendicular to the plane. In my case, it is the plane of whiteboard, and directed outwards. Right, students? And this I will indicate with the help of this symbol. So if I denote it like this, it suggests that the direction of the magnetic field at point P is perpendicular to the plane of the whiteboard and directed outwards. Right? While at point Q, what will happen is the field line will enter point Q. So at point Q, the direction of the field line would be perpendicular to the plane and directed inwards. So at point Q, the direction of magnetic field is perpendicular to the plane and directed inwards. And this is the symbol I will be using. So this is the symbol to represent that the magnetic field is directed perpendicular to the plane and in inward direction. In your case, it would be perpendicular to the plane of the paper, right? So students, let's apply, this is point A and this is point B. Let's apply this rule and find the direction of the magnetic field at point A and B. Now look, current is flowing along this direction. So from point B, the magnetic field lines are coming out, and to point A, it is entering. So at point B, the direction of the magnetic field would be perpendicular to the plane and directed outwards. So it will be represented like this. And at point A, the field line is perpendicular to the plane and directed inwards. And that is represented by this symbol. So student, I hope it's clear. So this symbol is used to represent the direction of the magnetic field which is perpendicular to the plane and directed outwards. And this symbol is used to represent the direction of the magnetic field which is perpendicular to the plane and directed inwards. Clear, students? So magnetic field lines, they neither have any starting point nor do they have any end point. They are in the form of continuous closed loops. So again, let me state this thumb rule. It's very simple, students. Right hand thumb rule states that if we hold a current carrying conductor in the palm of our right hand in such a manner that the thumb points towards the direction of flow of current. In that case, the direction in which the fingers curl, that will give us the direction of the magnetic field. So in case the current is flowing along the straight conductor in the upward direction, magnetic field lines, it will be like this, in the anti-clockwise direction, like this. And whenever the field lines are curved, then at any point it's given by drawing a tangent. So at this point, it is coming like this. So at this point, it will be perpendicular to the plane and directed outwards. At this point, it will be perpendicular to the plane and directed inwards. Clear, students? So that was regarding right hand thumb rule. This rule is used to determine the direction of the magnetic field at a point due to a current carrying conductor. Clear? Okay. Now let's discuss, or rather let's draw the field lines for a straight current carrying conductor and due to a current carrying loop. Right? Although I have drawn it over here, but still I will draw magnetic field lines. They will be in the form of continuous closed loops. So first and foremost, we'll consider a straight current carrying conductor and we'll assume the current to be flowing in the upward direction. So, due to a straight current carrying conductor, we're discussing case A. Straight current carrying conductor. Okay. So, case 1. Suppose the current is flowing along this direction. So just to give it a three-dimensional appearance, I'll show it like this. Let us consider this to be a horizontal plane and current is flowing in the upward direction, say from X to Y. Right? So now we need to draw the magnetic field lines on this horizontal plane. So how to draw it? It will be like this. So these are the magnetic field lines. It will be directed like this. These dotted lines, which are in the form of continuous closed loops, they represent the field lines. And it will be in the anti-clockwise direction, like this. So these are the field lines. Right, students? So like this. It will be in the anti-clockwise direction. Continuous closed loops. So these are the magnetic field lines. Clear? This is a diagrammatic representation of the field lines due to a straight current carrying conductor. Right? Now, the second scenario. If the direction of the current is reversed, suppose now current is flowing along this direction. So let's plot the field lines in this case. Just to give it a three-dimensional effect, I am showing this particular diagram. Okay. In this case, the current is flowing like this. So apply right hand thumb rule. So it will be like this. The thumb indicates towards the direction of the flow of current. So the direction in which the fingers curl, that will give us the direction of the magnetic field. So in this case, the magnetic field would be in the clockwise direction, right? So it will be like this. I am representing it with the help of dotted lines. Do indicate these arrows. They represent the direction of the magnetic field. This is the direction of the magnetic field, which will be in the form of continuous closed loop and in the clockwise direction. So students, these are the magnetic field lines. I hope you have understood the concept. You can easily visualize the field lines due to a straight current carrying conductor, and I have elaborated both the cases when the current is flowing from X to Y or the current is flowing from Y to X. Clear, students? Okay. Let's discuss magnetic field lines due to a current carrying loop, right? So let's try to discuss the other case where instead of a current carrying conductor, we'll consider a current carrying loop. It can be a circular loop or it can be any closed loop of any irregular shape, right? So B is current carrying loop. Let us consider, just for convenience, a circular loop. Here also we'll consider two cases. One, when the current in the loop is flowing in the clockwise direction, and in the second case, we'll consider the current in the loop to be flowing in the anti-clockwise direction, right? So, again, just to give it a three-dimensional effect, I am using this particular diagram. This is a horizontal plane, and this is a circular loop, suppose. This is a circular loop. And let us consider this to be connected to a source. It is connected to a source, and this is the key, one-way key. So if it is closed, the circuit gets completed. The current flows from higher potential to lower potential. So in this case, the current through the loop would be flowing in the clockwise direction. Look, it's flowing in the clockwise direction. Right, students? So let's see how the magnetic field lines will be in this particular case when the current is flowing in a loop, and that too in the clockwise direction. Now we need to plot the field lines on this horizontal plane, right? So what to do is, over here, the current is flowing in the clockwise direction. So at this instant, the direction of the current would be like this. So apply right hand rule. So it will be like this. This is the direction of the current. So field lines would be like this. Field lines would be like this. It will come out from here and it will enter over here, right? At this point, current is in the downward direction. So it will be like this. Thumb is pointing downwards towards the direction of the flow of current. So the rest of the fingers, they are curling inwards like this. So the magnetic field lines will be like this. Here the magnetic field lines will be like this. And here the magnetic field lines will be like this. Am I clear? So let us draw the diagram. So it will be in this manner. These are the continuous closed loops. The magnetic field lines do not have any starting point nor end point. Okay, it will be like this, along this direction. Right, students? And over here, it will be like this. So it will be in the clockwise direction. So if you draw the magnetic field lines for this section, it will be like this. These dotted lines represent the field lines. So it will be like this. Clear, students? So you can well imagine this is the plane of the loop. From the front, it will appear as if the field lines are entering. It will appear as if the field lines are entering this loop. Clear, students? So these are the field lines which are represented by the dotted circular lines, concentric lines. Right? So let's discuss the second case. Here the current is flowing in the clockwise direction. Now we will consider the direction of the current to get reversed, and then we will try to draw the field lines for the current flowing in the loop in the anti-clockwise direction. So let's draw the diagram for that case as well. Again, let's consider this to be the horizontal plane, right? This is the loop under consideration. And here, simply, the polarity of the source is reversed. The polarity of the source is reversed. Now, this is our lower potential, and let us consider this to be at higher potential. So, the direction of the current will get changed. Now, the current would be flowing along this direction, in the anti-clockwise direction. Right? Okay. Now let's draw the magnetic field lines for this case. Again, which rule to be used to determine the direction of magnetic field due to a current carrying conductor? Yes, it's the right hand thumb rule. Here, students, look, current is in the downward direction. At this point, the current is in the downward direction. This is the current. Current is in the downward direction. So, let's apply this rule. Thumb pointing downward, that is along the direction of the current, and the fingers, the direction in which the fingers curl, that will give us the direction of magnetic field. So, it will be like this. So, the direction would be in this particular manner. These dotted lines will represent the magnetic field lines. These are the magnetic field lines. Right, students? Okay. Over here, the direction of the current at this point would be in the upward direction. So here, the magnetic field lines would be like this. Again, it would be like this. So let's draw the magnetic field lines for this part of the loop as well. So you can visualize the magnetic field. So from this face of the loop, from the front, it will appear as if the field lines are coming out when the current in the loop is flowing in the anti-clockwise direction. Clear, students? So 2 points can be concluded. There are 2 points which we can conclude from this diagram. If in a closed loop, the current appears to be flowing in the clockwise direction, then the field lines will appear to be entering the plane of this loop. While the second conclusion is, if in a closed loop the current appears to be flowing in the anti-clockwise direction, then the field lines will appear to come out of that plane of the loop. Clear, students? So these are the 2 very, very important conclusions. I hope you have understood the concept. So these are the 4 diagrams which you need to be very, very clear of. One is the magnetic field lines due to a straight conductor. There are 2 cases, the direction of the current, one is in the upward direction and the other when the direction of the current through the straight conductor is reversed. And the second is when the current is assumed to be flowing in a closed loop. One in the case of clockwise direction and the second is in the anti-clockwise direction. So students, in this session we have discussed Oersted's experiment, magnetic field lines and the plot of magnetic field lines. And obviously we have discussed the rule as well to determine the direction of the magnetic field at a point due to a current carrying conductor. So before we conclude this session, let me recap all those topics which we have discussed so far in this particular session, right? Oersted's experiment, magnetic effects of current was first studied by Hans Oersted. What he found was, when a current carrying conductor is considered, then the surrounding or the vicinity near the current carrying conductor is found to experience some magnetic effects. It will exert some magnetic force on some other objects which are magnetic materials, right? So when a compass needle is brought near a current carrying conductor, it will show some deflection. So what was the conclusion? A magnetic field is produced near a current carrying conductor, and this effect of current is known as magnetic effects of current. So students, later on as we go on with our syllabus, we will study that there is a very, very important link between electricity and magnetism. Flowing current, magnetic field is produced around it. moving magnet or changing magnetic field, that in turn will produce electric current. That is electromagnetic induction. That also we'll discuss in the later section. So electricity, magnetism, both are closely related to one another. Right? Then we have discussed magnetic field lines. Now look, these are imaginary paths. These are imaginary lines. It is a hypothetical concept. These are developed so as to visually represent the magnetic field lines. We can visualize the field strength of a magnetic field. So in a region where the magnetic field lines are crowded, in that region the strength of the magnetic field is much more stronger. Anyway, we'll discuss about magnetic field lines in the next lecture, right? About its properties and so on. So for now, you need to remember magnetic field lines are imaginary lines, or these are the path along which a hypothetical unit north pole would move if it is free to do so. Right, student? And magnetic field, it's a vector quantity. It possesses both magnitude as well as direction. The direction of the magnetic field at a point due to a current carrying conductor is given by right hand thumb rule. You have to make use of your right hand. So, if you hold a current carrying conductor in the palm of your right hand in such a manner that the thumb points towards the direction of the flow of current, then the direction in which the fingers curl, that will give us the direction of the magnetic field. So magnetic field lines, they are in the form of closed loops, and in case they are in the form of closed loops, they don't have any emanating, that is initiating or starting point, nor do they have any terminating or end point. Clear, students? And thereafter we have discussed the plot of magnetic field lines due to a straight conductor and due to a conductor which is in the form of closed loop. So that's it for this session, students. Thank you, and join me in my next lecture. Bye-bye.